The energy environment in the United States is evolving. Many of the relevant factors when parts of the grid infrastructure were built have changed. As of 2019, the Department of Energy stated that more than 70% of transmission lines and large power transformers were over 25 years old, with some of those more than a century old. Over that time, some small towns have become bustling cities. Increased electricity demand from AI data centers, electrification and onshoring have placed additional strains on the grid. Dispatchable energy sources like nuclear, coal, and natural gas have also been joined by variable sources like wind and solar. These are some of the factors that complicate the problem of managing transmission congestion and safely meeting energy demand across the entire grid. One solution to reduce congestion in high-demand areas is to build more transmission lines, but this is costly and time-consuming. Another solution is dynamic line ratings, DLR, which can boost transmission capacity without overstressing the system. The success of dynamic line ratings hinges on several key elements: accurate, localized weather forecasts, rigorous operational safety monitoring, including line sag and engineering assumptions, seamless compliance with utility cybersecurity and regulation requirements, and complete transparency to build confidence in the safety and effectiveness of the ratings. Transmission operators must carefully manage power flows to meet the demands of various grid users, while simultaneously ensuring they don't exceed the capacity of any single transmission line or grid element. Since generators like wind turbines have a variable generation capacity, and other power plants can take many hours to turn on or ramp up their production, grid operators must plan ahead to ensure they don't exceed a future maximum operating current or ampacity. This is complicated because transmission lines don't have fixed capacities. Instead, the current they can carry is limited by the conductor temperature. Excessive temperatures can weaken the line or cause it to sag dangerously close to trees, buildings, or roads. In some cases, other inline components, like buses, jumpers, or switches, can impose limits, but most often, the limiting factor is conductor temperature, which leads to excessive sag. Transmission conductors are heated by current flowing through the line and from the sun throughout the day, and cooled by convection, the movement of air around the lines, and radiative exchange, the heat dissipated to their surroundings. A larger current generates more heat, which increases the component temperature, unless it is balanced by additional convective and radiative cooling. Thus, the true capacity of the line depends on the environmental factors that dissipate the internal heating. Because environmental factors dissipate the heat in a conductor, the true capacity of a transmission line varies throughout the day, and as seasons shift with changing wind, sun, and temperature. Historically, utilities used static line ratings, a single conservative value, but this often significantly underestimates capacity and can overestimate on extremely hot days with calm winds. Seasonal line ratings can substantially boost capacity by changing the rating several times per year according to the local climate, but still doesn't account for daily fluctuations. Recently, the Federal Energy Regulatory Committee, FERC, mandated that utilities adopt and use ambient adjusted ratings, or AAR, to increase capacity by taking ratings one step further and updating them each hour to account for changes in air temperature and solar irradiation. All of these methodologies leave out wind, which is the most significant cooling factor. Dynamic line ratings take this final leap to forecast the true line rating throughout the day. For safety, static and seasonal line ratings assume near-calm conditions almost everywhere in the continental U.S. Even the windiest places, such as Laramie, Wyoming, experience calm conditions nearly 5% of the time. However, the variation between these rating methodologies differs significantly based on location. In Laramie, the average wind speed is more than 12 miles per hour, while in Oak Ridge, Tennessee, it is calm 63% of the time with an average wind of only 2 miles per hour. These differences make a huge impact on the line rating. These typical conditions account for up to a 50% difference between the average ampacity in Laramie versus Oak Ridge. Local wind conditions don't just affect line ratings on conductors in different regions thousands of miles apart. They also strongly impact different spans along the same transmission line. Some spans may experience strong cooling winds, but others might be sheltered in valleys where the air is still. Because electricity flows evenly through a line, the component with the lowest ampacity at any given moment becomes the limiting span, the weakest link that determines the capacity of the entire line. This bottleneck isn't static, it moves throughout the day as the weather changes. And surprisingly, neighboring sections of the same power line can have significantly different capacities due to the effect local terrain, trees, and even buildings can have on the wind at each individual span. We can place sensors and weather stations along the transmission lines to measure the conditions and provide a safety check on conductor clearance limits. However, because power plants can take hours to change load, transmission operators and dispatchers can't rely on just the current line rating. They need to forecast it. Challenge 1. Since sensors and weather stations can't measure the future, we need a way to translate current observations and weather forecasts into confident future predictions of the line rating. Regional weather forecasting models, like the High-Resolution Rapid Refresh, pronounced HRR, are among the most advanced tools we have for predicting short-term weather. The supercomputers that run these models perform atmospheric physics calculations on 1.9 million grid cells as small as 3 kilometers to predict future weather. This takes a lot of computing power. Models like HRR can use around 50 petaflops of computing capacity, or the equivalent of 10,000 laptops. Even with massive supercomputers, weather models still face limitations. Within a single 3-kilometer grid cell, complex terrain and surface features can substantially influence the weather. Wind rushes up small valleys when heated during the day, canyons channel it, and mountains can block it. Evaporation from rivers, lakes, and vegetation cools the air during the day, while roads and rocks may heat it. These subtle variations can have a profound impact. A 30-degree difference in the wind direction can change the rating by 41%. A 6-mile-per-hour wind speed change can change the rating by 150%, and a 5-degree temperature change by 4.5%. Consequently, it's extremely important to account for local terrain features. Weather forecasts are often inaccurate, which is why we also need to know the uncertainty associated with a prediction. The HRR tends to overestimate low wind speeds and underestimate strong winds, potentially causing transmission operators to overload power lines due to overestimating their capacity. Statistical weather forecasting is challenging due to the variability of weather over time and space. While weather stations provide accurate measurements, the accuracy of predictions decreases as we forecast further into the future, and conditions become uncertain as we move further away from them. To forecast DLR, we need to confidently predict extreme weather conditions and ensure enough weather stations for accurate measurements across a given area. To understand the level of uncertainty in a forecast, larger global models perform multiple parallel simulations, known as ensembles, each starting with slightly different conditions. The Global Ensemble Forecast Model, for instance, is made up of 21 ensembles. This is where statistical forecasts like hurricane paths or percent of rain come from. The cost of running multiple simulations forces these statistical models to use much larger chunks, so they can't provide a detailed local forecast and don't account for the impact of terrain. The HRR model drastically increases resolution, but requires so many computational resources that running multiple ensembles isn't cost-effective. Consequently, it provides only a single forecast. For DLR, we need to both accommodate for the impacts of terrain and get a statistical forecast. Fortunately, recently emerging methods leveraging AI and machine learning can bridge this gap by looking at patterns in weather observations and forecasts. More about this later. Weather station data can greatly decrease forecast uncertainty by comparing current observations to historical forecasts. This data can also be incorporated as initial conditions and corrections to forecasts by integration into NOAA models. So having more weather stations improves both our understanding of the forecast and the forecast itself. Properly accounting for localized weather variations and statistical uncertainty in the forecast provides transmission operators with a tool they can utilize to confidently use future thermal line ratings. Weather isn't the only challenge in delivering safe, dynamic line ratings. Even the perfect forecast could result in disaster if our assumptions about the conductor conditions are wrong. As conductors become fouled and age, their mechanical and conductive properties change. A fouled conductor actually loses more heat due to increased radiative emissivity, which can be as much as a 10 to 14% difference in calm wind conditions. According to the Electric Power Research Institute, many utilities presently overestimate the radiative emissivity, increasing the risk of inaccurate ratings. Another challenge, known as creep, actually elongates the conductor over time due to temperature cycling, ice loading, and continuous tension, which can decrease clearance and increase how much conductors sag as their temperature increases. Excessive unpredicted line sag has caused many of the largest outage events in the world and been a contributing factor in many transmission-ignited wildfires. Consequently, if lines are to be operated near their maximum design capacity, it is important to monitor their sag and evaluate the underlying engineering assumptions. A safe and capable DLR solution requires many elements. First, it requires a robust weather system that is localized enough to account for terrain and can assess the uncertainty of the forecast, along with adequate weather stations to inform and improve both of those. Second, if operating close to the maximum capacity, it requires safety precautions, including real-time line sag monitoring and assessment of underlying engineering assumptions like line emissivity and conductor strength. Third, it must effectively integrate and scale to accommodate utility needs. This means meeting regulatory and cybersecurity requirements. For FERC 881 compliance, a utility must cover the entire system, including inline components and all lines, so the DLR system must be cost-effective and easy to install. Finally, it cannot be a black box. Utilities must understand the limitations of the weather forecasting and model assumptions, as well as understanding the context of forecast weather conditions. Available DLR solutions come in many forms. Sensorless solutions may rely on existing weather stations and have advanced forecasting tools, but be inappropriate in rural terrain and cannot monitor line sag or validate engineering assumptions used in the line rating computations. Remote sensing systems such as LiDAR and millimeter wave radar can provide safety monitoring, but lack the tools to provide line rating forecasts and their associated uncertainty. Line contact sensors also provide effective line safety monitoring, with some ability to determine weather conditions by inferring wind speed through conductor vibration, but still need additional weather tools to assess other weather variables and provide forecast data. Pitch Aeronautics WireWeather software and WireWarrior sensors can address all of these challenges of implementing DLR. It is a scalable solution that can be configured for the entire network and all inline components. We aggregate weather station and weather forecast data in the service territory for the past several years and run high-fidelity wind models on the terrain. We use this to train an AI/ML model to predict high-fidelity wind fields. This AI/ML system is unique in that it assesses the accuracy of its own prediction using a mathematical technique called a Gaussian process. The output from this model includes high-resolution forecast information and the uncertainty in that prediction. WireWeather uses this to generate a statistical forecast of thermal line ratings at every span within the transmission network. This instantly provides DLR and AAR for the entire transmission system, which can be used for regulatory compliance and the confidence to manually use higher ratings for contingency operations. This provides analytics on every line within the system. The WireWeather model can also identify areas with high weather uncertainty or lines that are likely to be operated near the maximum operating point, where Pitch Aeronautics can install our WireWarrior sensors. The WireWarrior is first and foremost a weather station that precisely measures winds, solar irradiation, temperature, humidity, and atmospheric pressure. The WireWarrior also includes a downward-facing millimeter wave radar, which can measure the distance of all conductors to the ground with millimeter accuracy. This provides safety monitoring and allows us to approximate the heat transfer characteristics of the conductors. The sensor also can monitor and pinpoint sources of partial discharge to help identify broken insulators, stranded conductors, and other reliability problems. Data from the WireWarrior is encrypted and sent over cellular or satellite networks with a unique authentication key to the WireWeather software database. WireWarriors can be quickly and safely installed with Astria, the only US-made drone capable of line-to-line installs. All of this data is directly visible in WireWeather and decreases the uncertainty in the weather measurements and provides line safety observations from the field. As needed, Pitch Aeronautics can integrate the ratings onto on-premise networks with a cyber-secure integration client to provide ratings directly to the EMS or customize solutions to meet an individual utility's needs. Implementing dynamic line ratings presents many challenges, but using Pitch Aeronautics' WireWeather and WireWarriors provide utilities with the tools to implement DLR and optimize the use of their existing infrastructure to significantly enhance their transmission capacity. By leveraging real-time weather data and advanced analytics, these solutions allow utilities to dynamically adjust the line ratings based on current and future conditions. This ensures that the transmission lines are operated at their maximum safe capacity, maximizing efficiency and reliability while minimizing the need for costly infrastructure upgrades. Overall, Pitch Aeronautics' WireWeather and WireWarriors play a key role in enabling utilities to adapt to the evolving energy climate and meet the growing demands for clean, reliable, and affordable electricity.